All right, now that we have taken a look at an implementation overview, let's go ahead and get started with the real planning for our precision game. Now, let me go ahead and warn you, some of these videos are going to get long. Starting with this one. This is probably going to be a half an hour, so if you need to go get some coffee or some soda, do it now. Now, what we're going to be doing in this video is taking a look at part one of our implementation plan. Now, if you recall, part one consists of creating, let me go ahead and grab a pointer here, creating the skeleton classes with members. So what we're going to do is we're going to walk through all the classes that we're going to need, and we're going to talk about the members that they need, etc., etc. So a lot of different things for us to talk about in this video, but this is what we're doing. We are addressing the implementation plan for part one. So let me go ahead and bring up a new whiteboard. So we'll go and hide this guy out. We'll jump all the way back up here to the top, add a new one in, and we're ready to go. All right. So as a reminder, part one, skeleton. All right. Before we jot anything down, we need to talk about what kind of classes we're going to need. It's obviously important to have some sort of idea of what the classes are going to be before we start creating skeleton classes. So what are we going to need? Well, we've got a player, we've got enemies, we've got cells, we've got these life bars and time bars for the power-up, and, well, we have a power-up itself. Now, we're going to address the power-up at the very end of all this. Remember, we are addressing that as if we were just going to add some sort of enhancement to the game after the game is completed. So we will deal with time power-ups and power-up systems later. For now, though, we need to focus on the essentials of the precision game. So what do we need? Well, player, enemy, and cells. Well, do they all share anything in common with one another? Well, of course they do. Player, enemy, and cells are all going to have things like a texture, a location, perhaps an origin, perhaps color tinting. I mean, there are definitely a handful of things that the different elements on the screen that will be interacting with one another, player, enemy, and cell, are going to share. So what we're going to do is we're going to use a breakdown that's very familiar. We've used it throughout several of the applications that we've written. Basically, we're going to do the following. We're going to start with a base class that's our actor class. An actor is going to contain things like the texture, the position, a color tint, an origin, radius, etc. Now, we're going to extend actor into classes that are a little more defined, such as our player, our cells, and finally, our enemies. Okay. Now, of course, there's only going to be one player with the way that we are creating the precision game, but there's going to be multiple cells and there's going to be multiple enemies. Now, the player, the cells, and the enemy will all be inheriting everything from actor, so they're all going to have textures, positions, etc. Okay. Now, one of the most important things that we're going to do with actor, though, and once again, we have seen this in the past, is we are going to create a static list. And that list will hold a list of actors. So everything that we create, if we create, here's our player, so we'll call it player. And then here's enemy 1, 2, 3. So we'll just call this E1, E2, and E3. And then a bunch of cells. Okay, so C1, C2, C3, and C4. All of this will be logged in a list. Okay, so you'll find all of these actors in here. So player, E1, E2, ... all the way down to C4. So now we can easily loop through this list and update cells, or loop through this list and deal with enemies, or find a player if we need to. Though we're also going to hold an external reference to the player as well, just to speed things up, and you'll see what we're talking about a little bit later. But the actor needs to hold a list of all actors that are roaming around in the game. Right, Logan?
Right, the idea here is that we hold a static actor management system is what we use to control and to work with all the actors that are created. And the idea is that this management system reside in the actor class itself so that everything is neatly contained. That way we don't have the actor purely representing the, the instanced methods and all the instance fields. Instead, it holds both the static and instance fields. So that way it holds the information necessary to instantiate a new actor class as well as the static management system. So everything is packaged up into actor.
That's right. So we need to start this whole thing off by adding classes. And the classes that we're going to be adding are going to be actor, and then off of actor, we're going to have player, enemy, and finally, cell. Okay, an actor is going to have a collection held within it. So I'm just going to write down collection. So I'm going to start throwing the word collection out because they're going to see this in upcoming volumes of XNA. Now, we also have bars, these life bars that the cells have that are going to appear in the game when a cell is dying. So what we're going to do is we're going to create a class for bars. So let's go ahead and jump all the way over here. This is going to be our bar class. Make that look a little bit nicer. There we go. And inside the bar class, guess what it's going to hold? It is going to hold a static list of bars. So here we are, bar, bar. So we got two cells that are currently dying at the moment, and they have bars up underneath them. They have their life bars. So here is life bar for cell 1, and here's life bar for cell 2. Basically, for updating all of our bars, we can now simply walk through a static list, and there's all of our bars with all of the relevant information available right there. So we're going to have a bar class. Is that pretty clear, Logan?
Right, and it's the same idea of the static management system.
Exactly.
Since bar is going to be significantly different from an actor in that it's going to have a changing size, a changing area that it actually represents, it's significantly different from actor and its positioning and properties. But it also has to have or handle the concept of multiple bars. And just like where we package everything in actor, we're going to do the same thing with bar. While bar will contain all the instance methods and fields, it will also contain the static bar management system.
That's right. But there's enough differences between bar and actor that bar did not need to be a class that extended actor.
Right. It's completely different in the way it's placed. It has alignment abilities.
That's right.
And also, the fact that the lists are separate is actually beneficial when we get back to the main game class and we want to draw, because we have all the bars in one group or one list and all the actors in another group or another list. We can control their draw order much more easily. So that way the bars and the actors can be drawn on, you could say, different layers without actually having to get into a layer layer implications.
That's right.
We can just draw them in order of the correct one in order, and then everything works.
And there you go. Exactly. Which we'll actually point that out much later on in this series when we get to that area.
Right. You could get into a finer level of control, but what's nice is separating these two. What I was trying to say earlier is that separating these two avoids the need to get into complicated layer settings.
Yeah.
Instead, we can just handle them as two different groups.
Exactly. Okay, so now these are the classes that we need. So in establishing the skeleton framework for precision, we'll begin by adding these in. Now let's see. What do we want to do? Let's go ahead and start focusing on the members of the classes. So we'll start out with the actor class. So what are we going to find in the actor class? Well, let's start out with fields. So first of all, it's going to have the static, and guys, I'm going to abbreviate a lot of this stuff, so please keep that in mind. But static list, it's going to, of course, be public. That's what I mean by abbreviating. So static list of actors, and of course, actors. So that we have a place where we can store all of our actors. Now, we've got some other guys that we're going to need. Like I said, we're going to have a position, which is going to be a vector 2. We're going to have a texture. So each actor has a texture. So it'll be a texture 2D. And we're going to have a tint.
The importance of having the tint is that will allow actors to support the modulation color when being drawn. This is very important because we've noted that the cells have to change in color as they die. They have to go from a healthy color to a dead color. And we need some place to store the current color. Well, we know we have two colors at this point. We have a healthy color and a dead color. The problem is we have another one. We have what the current color is, and that can be held in tint. What is this actor's current modulation color at the given moment?
Exactly. So now here we are with fields. Well, and that's pretty much it. Now we need properties because, well, we want to give ourselves some sort of way of accessing these fields, but now we're going to start making things, like in this particular case, we're dealing with the position. We want the position to be private. We're going to have the texture and the tint be protected in case any further extended class can make use of them. But we don't want anyone outside of this world being able to directly access these fields, so we're going to start setting up properties. So let's go ahead and throw properties in here. And the properties that we're going to have, of course, is going to be a position.
Now, and of course, just being a simple accessor to the position field.
Exactly. Now we're going to have a couple that you might not be expecting. We're going to have an origin. And with the origin, basically, this is just going to be a calculation. So you'll notice it's not tying into a field above that's called origin. Instead, what this is going to do is it's just basically going to deal with our texture. So it's just going to turn... It's going to be the 1/2 the width and 1/2 of height.
Right, since we have no use for an adjustable origin per actor.
Right.
Meaning we're never going to move the origin around. What we're going to use the origin for is so that all drawing of actors can be centered.
Exactly.
So basically actors are drawn around their center. So really origin could almost be thought of as a property called centered origin.
True.
And for centered origin, well, we want to get the center of the texture, so we do that calculation. We get half the width, half the height, and that is the centered origin that we're looking for.
Then from there, we're going to have another calculated property, and this one is going to be the radius.
Now, where this property came about is the fact that early in the design phase for precision, we decided that we wanted the collisions to be simple. We wanted to do distance-based collision. And in order for that to work smoothly, most or all of the actors have to be generally circle-shaped, so that from all sides you can do a simple distance check. Now, in order to go hand-in-hand with the distance check, it's helpful to have the radius of each individual actor.
Okay.
So that way we can say when the length of one radius and the other radius are close enough that they would overlap, then we have a collision. But having a radius property instead of having to look at different sides actually makes this calculation a lot easier. Since we can just look at it, it's basically say, pretend that this actor is in fact circular. Now get the radius based on the texture being used.
Exactly.
That's the value we'll use for collisions.
And if we just grab 1/2 the width of the texture, we've got a simulated radius.
Right, providing that texture was generally circular.
Exactly. Okay, so now we've got that, and that's going to be it for our properties. So now let's take a look at a constructor. We're going to need both a public constructor and we're going to need a static constructor. So I'm just going to put public/static. That's an A, honest, constructor. Let's go ahead and make it plural because there are two of them. And basically what needs to take place here in the static constructor, we're going to create our list. And in our public constructor, I could flip these so it would basically go hand in hand. Our public constructor is going to take in the texture.
The idea is to set it so that each actor takes in a texture on creation, since that texture field has to be populated at some point in order for drawing to work.
That's right.
And since I don't want to have to come up with a complicated mechanism for handling a null texture, instead I want to set up to where you have to provide a texture at actor creation time. It just makes things easier to manage a little bit later.
Exactly. So there you go. While you were talking, it just gave me a little extra time to write this out. So in the public constructor, we'll be taking in the texture 2D. In the static constructor, we will, create our actors list. All right, so constructor's out of the way. So now what we can do is, of course, by putting this in, now the interesting thing is all of our other classes that we've put in, the player, the enemy, the cell, well, they're going to need to make sure that they pass that texture 2D along all the way back to actor, because actor is now expecting that in its constructor. So we're going to need to make sure to implement constructors in player, enemy, and cell that take in a texture.
Right, since this leaves no default constructor, that means one has to be specified. So the moment we add this and try to build, it actually breaks the player, enemy, and cell classes. But of course, to fix that, all we have to do is go into each one of those and give a constructor that will satisfy the public constructor of actor.
So I'm just going to say fix all descendant classes. And I'll just put constructors as no.
Right, just so that we can, from this point forward, continue to build the solution.
Okay. All right, so with that in place, now we get to move on to our methods. So what methods will the actor need? And I'm going to go ahead and scroll down just a little bit because we're going to need some room here. There's not too many. Update. Update's going to be very important. Update's going to be critically important because we are doing a lot of time-controlled elements, a lot of things like time bars are going to need to be updated, scaling, that's going to, a lot of animated things. That's the best way to put it. So time's going to become critical. So what we're going to do is we're going to have an update method that's going to be virtual so that the player can have his own version of update, so it can handle particular things like invincibility. Cells can have their own version of update so that they can handle things like color changing or whatever. You get the idea. So we're going to have a virtual update, which is going to be extremely important.
Right, it's like you said, it's going to be the heart of any time-based action that needs to take place in any actor or anything that descends from actor.
And I'm actually going to throw this one in there because time is going to become such an important element of precision. It's going to be taking in a game time. So I'm literally just going to put this there right now just as a reminder.
Yeah. The idea here is also that this update method is to be called from the game's own update.
Right.
Since that's what's going to originally provide the game time or game time struct itself is going to be update. So we need to get that passed along. Really, it's kind of a passer. It's in the light that the game itself has an update, which is where you generally handle anything time sensitive. Just take that and pass that along to actors. So actors are updated along with the game using the same game time.
Now, once again, I am abbreviating here. I'm just going to write sprite batch. I'm not putting the full signature in place, so keep that in mind. So where I did put the full signature in place for update, I just want everybody to keep in mind this is just a quick abbreviating, so I don't have to write as much. But we're going to have two methods, one called draw actors and one that's just simply called draw. And here's why. And draw is going to take in also a sprite batch. Basically, in draw actors, we're going to have a loop. And we can loop through all of our actors in our static actors list. As we get to each one, guess what we can do? We can draw the actor. So we can call upon the draw method to actually handle the drawing of that particular actor. Okay? So that's how those two methods are going to work. Now, we've got just a couple more things that we're going to throw in there. We're going to throw in a static. So this method does not belong to any instance like of a player or cells or enemy. It's just sitting out there at the class level. We're going to create a static check collision. And with check collision, we're going to be able to say, here's actor A and here's actor B. Do they collide? Yes or no?
Right, this is going to be the heart of the collision system within precision. Now, since the collisions are as simple as they are, distance checks really, we don't need to dedicate a lot of code to a complicated collision system. It's just a simple mathematical check between vectors. But the functionality is being placed in actor itself since there is no external method. There's not enough code to warrant having an entire class dedicated to it. So since check collision is based around actors and the properties they contain, it's actually going to be placed into actor as a static method. So it can be viewed as a utility method in that light. And
right.
That anything with access to actor should be able to do a check collision between actors. But the code is physically located inside of the actor class.
Exactly. Now we've got one more check collision that we're going to put in here, and this is a special case check collision. We'll go ahead and jot it down, then I'll talk about it. So it is check collision with any. And notice how we don't have static in front of this. Basically, we can say with any cell. So here I am, a particular cell. I want to see if I am colliding with any other actors. And we're going to use this particular method for laying down our cells to make sure that the cell's not overlapping with any other cells.
Right. The idea is that every time a cell is placed down, we want to make sure that it's not been placed on top of another cell. Now, to do that, since all we're looking at is the cell we just created, we have to loop through everything else to see if it's colliding. Now, this could be accomplished without even using this method, but that means outside of actor we would need a loop and some checking system. That means the loop would have to look at all the actors and do the proper comparison, fill in actor A and actor B. What check collision with any can do, since it's instance, is it can hand itself to maybe actor A, and then it can do a loop and hand all the other actors to actor B and use the existing check collision. So it's basically an additional control system over check collision so that you can ask any specific actor if it is colliding with any other actor.
Now, let's see if we can squeeze a little bit more onto this screen. That's it for the actor class. So what I want to look at now is going to be the player class. So once again, what is the player class going to need that is going to be, well, more specific than what was available in the actor class that, in the end, will define the player? Well, for fields, it's going to need an invincibility time. So this is going to be a float. I'm just going to write invincibility time. Invincibility time is going to basically denote how many seconds our player is invincible. So most of the time, this is going to be at 0, because obviously when we're playing the game, we're not invincible most of the time. What's going to happen, though, is when the player resets, remember, we end up in the center of the screen, and we flicker for a second, and that 1 second, while we're flickering, that means we're invincible, which means we cannot be harmed by any of the antibodies. So invincibility time, this is where we're going to set. This is how long that we're invincible before, and we're going to start counting this down. We're going to chip away at it.
Right, that's what's interesting to point out, is that invincibility time represents the invincibility time remaining. So what this is used is both as a setting and as the check for is invincible.
Exactly.
The idea is that if invincibility time is greater than 0, then the player is currently invincible. Now that amount of time, instead of representing a setting, is instead decremented. So that value is chipped away at as time passes until it reaches 0. So invincibility time may start out at a full second, but then as a few milliseconds go by, it gets taken down. So maybe it's now 0.9 seconds remaining, and continues to decrement until it runs out. Once it hits 0 or less than 0, then that means there's no invincibility time left, and the player becomes not invincible anymore.
Okay. Now we have a property that also works with invincible, and the property is called isInvincible.
So it's kind of a trying to take an efficient look at using fields, because of course both invincibility time and isInvincibility could be simple fields, but the key here is that a simple check can yield this value, meaning that if there's invincibility time remaining, the player is invincible. If the time has run out, then the player is not invincible. And what's nice is this way we don't have to worry about a field that has to be set and a possible area for problems since we have to remember to set the field.
Right.
Instead, we just look at the time. Is the player still invincible, yes or no?
And so, yeah, it's going to return a true or false. All right, so this is going to bring us to what methods are needed by our player. And, well, first of all, we're going to need an update. And so this is going to be our override update. Actually, let me back that up, too. It'll look a little bit nicer if I do this.
Right, since player is an actor, we're going to override update so we gain access to some time-based functionality.
Ooh, which we're going to need because that's where we're going to chip away at that invincibility time. And if there's no invincibility time to chip away at, then there's nothing that we really need to worry about doing. Right. So there's nothing that's going to take place.
It's just there so that we can chip away at time if necessary.
That's right. Okay, and we've got one other, and we just said it a second ago, and that is basically when the player is reset.
So reset's going to be an actual method, something that the player can do, so that you can take the player, call upon it, and say, all right, reset, which should handle things like repositioning at the center of the screen, and it's also going to take in the amount of invincibility time that the player should gain from this specific reset. That way we don't have any kind of gameplay property stored inside of player. It can be stored inside of game. That way the game can tell the player, all right, reset, and then read its property and say, all right, reset, okay, the player invincibility time is supposed to be this, and pass it along.
Exactly. So that is everything that the player is going to have. So we've looked at the actor. We've looked at an extended version of the actor, known as the player. So now what we need to do is go ahead and take a look at the enemy. And enemy is going to start getting into a few more things than what player had. So let's go ahead and just jump back up here and add another sheet to our whiteboard here. Good old Photoshop. All right, so let's jump up here to the top. Enemy class. Once again, an extended actor class. So the enemy class, let's start out with what fields will the enemy need that will make it different or a little more defined from just a generic actor. Well, we're going to start out, and let's just back up for a second. Let's think about this. Enemy needs to be able to move around the screen. He's not under the control of a human being that has an Xbox 360 controller and is manipulating its position. Instead, it's got a very, very basic form of AI that's moving around. But AI is going to need to know a few things like how fast can he move? Can that speed vary any? When he scales, what speed is he going to scale up? Because remember, when they come into existence, they scale from 0 up, so they grow. It looks like they're climbing out of cells. We're going to need to know these kinds of things. So we could start out by first just creating a constant, and in that constant we can go ahead and hold the scale time, and we can use that scale time to basically determine how many seconds will it take to scale up. So let me go ahead and write that one down.
Right, we'll hold that as a constant, so we have an easy to identify variable, or field, so that later in code we can turn on and use that when we get to the scaling portion. So that when we decide that, alright, we're making a new enemy and we need to have it fade in, here's the amount of time it needs to fade in for, or needs to scale over.
And once again, this is in seconds, so I could say something like equals 0.5 float, and we have a half a second scaling time. So half a second, it'll scale up. So let's see, what else do we have? So let's get away from our constants. That's the only constant that we've got going. Now, like I said, speed. So we need to know a base speed and some sort of speed variation that can take away or add to our base speed. So we're going to have some private floats for base speed. And a speed variation. We're also going to need to figure out some sort of system and how we're going to move our enemy around. And this is going to be really important. The way that we're going to do this is basically we're going to have kind of a point A, point B type system. So the enemy is going to start here, and the goal is for him to get here. So we have a distance to travel, starting at 0% traveled to 100% traveled. And then we have a certain amount of time that we're looking at for the enemy to get from point A to point B. And then, of course, now we've got to take into account speed and all to make this happen. So we need some way of generating a point A, a point B, and we need some way of knowing what is our move time that we're looking for. And we need some way to deal with the amount. How far along, percentage-wise, are we from A to B? So there's quite a bit of stuff going on here. So we're going to need a few different fields for this. We're going to need, well, let me just go ahead and put them down. We're going to need a vector to point A and point B, and that'll hold our positions. We're going to need a float that's going to be amount, and this is the percentage between points A and B. And we're going to need a float that holds the move time, and this is the amount of time to move between A and B. So let me go ahead and jot all that down.
Right, and the idea here is to have basically a more wandering style system without having to get into specifics on direction and things like that. The idea here is that it's very easy to generate a random point on the screen. It will probably already be in use. Is it in use at this point? Well, either way, it's that would be one of the easiest ways to generate a position. Now, the catch there is if you just change the position randomly, you'll end up with an enemy that will simply teleport location to location. Right. So the idea here is that we instantly generate a new point for the enemy to move to. But then we need some type of time control system so that we can say, over time, how much has the enemy moved from one point to another? So that's where we'll generate the point instantly, but then it will take an amount of time to get to that point. And then in order to make a continuous navigation, the idea is that once we have finally navigated to point B, then we regenerate the point B again. So A becomes where we're at now. A is the current point, so basically B becomes A, then a new B point is generated, and then the enemy moves to that. So it's like this continuous move to a point, regenerate a new target, move to that target, regenerate a new target. And that provides the enemy wandering around the screen type of movement.
Woo. There we go. So all of these guys here work as part of the enemy movement system that we're going to be coming up with. Now, of course, we're going to need a constructor for the enemy. We already know that. We're already going to have one in place because it's going to need to take in that texture that it's going to need to pass on up to actor. Just go ahead and throw constructor in here because we need some other stuff too.
All right, the base speed and the speed variation need to come from somewhere.
So that's where we're going to be taking in our base speed. And our speed variation. So if we wanted to, every single guy could have its own base speed and its own speed variation, giving a wide arrangement of different speeds. Now, methods. What kind of methods will the enemy need? Well, not too many. First of all, we're going to have a set random move, and this goes back to what Logan was just talking about a second ago while I was jotting things down, which is we need to generate a new position. Like, let's say we've just gone from A and we've gotten here to B. Now what we need to do is make this B our new A, and we need to generate another B somewhere that we can begin working our way to.
All right, it's basically a way to reset the movement variables, or excuse me, the movement fields in such a way that a new move will occur from the current location to some new location. It's the mechanism that allows this move to begin over and over again for each, if you want to call it, individual movement.
And it's just going to be called set random move. It's, of course, just a private method, and that's what it handles doing. Now, of course, an update. We need an update here. So it's going to be another override update. And I'm sure everybody has figured out why update is so important to the enemy. We need to move the enemy over time. We've got this whole move system that we're establishing where the enemy is going to be moving, and based off of amount and move time and our point A and our point B and speed and all. So obviously, in update, this is where we're going to handle moving the enemy along. Okay?
Right, we need something that will be hit over and over again and will give us the amount of time that has passed, so that we can use that in conjunction with our own move time to increase the amount.
Exactly.
So that way we use the amount of seconds elapsed combined with the move time, which tells us how fast we need to move, and use that to cause the amount to increment.
You got it. Now, next one, and final one actually, is going to be a static. So once again, it's more like a utility method here. A static add enemies. So add enemies, basically I can call upon this method by saying enemy.add enemies. 5 enemies with this texture, this base speed, and this this speed variation. So then it knows that, well, we need to generate 5 enemies, and then, well, now we have the texture, we have the base speed, and the speed variation, and all that information is required for the constructor. So when we create them, we have the information already to hand to the constructor so that everything is happy.
It's almost like an extension to the constructor itself.
It really is.
It's a form of the constructor that lets multiple things get created instead of one.
So I'll just jot those down in here.
So, I mean, num enemies is going to be the whole key to add enemies.
Yeah.
The reason for it to exist is that way we say, well, all at once create 5 enemies.
And here's the texture. Here's the base speed.
Right, like you said, all the things that are necessary to satisfy the constructor so that we can go about creating the cells internally. But the things we gain from this is, 1, we can create multiple, and 2, they can be placed randomly. So this is where the actual random placement code. So why enemies, when created, because the constructor isn't actually going to deal with positioning.
That could actually cause a problem if it did, wouldn't it?
Well, if we left the constructor alone, if we went somewhere else, made a loop, and created a bunch of enemies, they're all going to start from position 0, 0, or the top left of the screen.
Mm-hmm.
Now, add enemies can address that by saying, let's say add enemies makes initial, or sets the enemies at each level begin, where the enemies need to start out already randomly placed onto the playing field.
Mm-hmm.
So that means that enemies could add the enemy, which technically means it's at 0, 0, but could immediately turn around and set a random position. So now, after add enemies is run, we have 5 enemies that start randomly, instead of 5 of them starting in the corner and then spreading out.
Exactly. Now, imagine if we left it up to the constructor to handle randomly placing the enemies when an enemy is created. What kind of a headache would that be when a cell died and we wanted an enemy to be spawned coming up out of that cell? Well, that's going to be kind of difficult because it's going to be randomly placed elsewhere if we left the enemy's constructor to handle that. And that would be kind of messy. So add enemies is going to take care of all of our random positioning when we need random positioning to occur, which is at the beginning of each of our levels. All right, very good. So that's going to take care of everything that we need in enemy. Let's go ahead and pull up another sheet and start talking about what's going to be required for cell. So moving right along, we're getting there, guys. Here we are with our cell class. Again, another extension of the actor class. And we're going to start out here, before we start talking about our fields, we're going to have a cell state enum. And this is going to become really important because cells can be in various states.
Right, and the interaction with cells is dependent on their state. And what happens to a cell is dependent on its state, meaning that a cell can't be saved if it's healthy. If it's healthy, there's nothing to do about it. A cell can only be saved when it's attacked. Also, a cell only loses health when it's attacked. And also a cell needs to be put into a save state so that we know that it's going away. And it also needs to be able to be put in a dead state. And in that state, it should be drawn a certain way and then is otherwise non-interactive once again.
Exactly. So this is going to become very important that we have these states in place. So we're going to set up an enum for this. Now let's go and start taking a look at the fields that cells are going to have. All right, what fields are required? Well, once again, we're going to start out with a couple of constants. We're going to start out with a cell save time, which is going to control the cell shrinking time. And we're going to have a cell placement retry count. Remember, when we go through and we randomly distribute cells throughout a level at the very beginning of the level, right before you start playing it, we don't want to run into a situation where we've got a player who's so good he's managed to work his way up to having a ton of cells on the screen and we get ourselves caught in an infinite loop because we just can't find another place to put a cell. So we only want to retry X number of times, and we're going to hold that X number of times in this field I'm about to write down. And once we have exhausted that, then we simply won't worry about it. Okay? So let me go ahead and jot these down.
All right, and the first one of those, the cell save time, like you had said, the whole idea here is that cells, when saved, don't simply disappear off the screen. Instead, they have a kind of scale-out effect. That effect needs to take an amount of time, and this amount of time will be defined here. It will be defined by a constant, so we have an easily recognizable label that we can use later in code.
That's right. So I run over this. This is how long it will take that I, as the player, just ran over this cell and saved it. How long will it take for this guy to scale down and disappear? And then the other const.
And that is the cell placement retry count. Again, that's more of like a give-up threshold, since the placement system is going to continue to try to place cells. Every time that it places a cell in a bad location, it's going to try again inside of a loop. And if there isn't something to break that, you could get into an infinite loop scenario. So basically, we want to set a threshold where after this amount of retries, the system just gives up. So that means there is the possibility that two cells could overlap, but they probably won't. After 100 retries, surely it'll find a place to put it on a generally empty board.
Right.
Now, if you get it to some insane level, yeah, sure, some things will start to overlap. But that generally won't happen until you get into incredibly high levels.
Exactly. So in this case here, in fact, we're going to use this in the game. We're going to set the cell placement retry count to 100. And what we're saying right here is, hey, try 100 times and then afterwards give up. And hey, we can even go back and visit this constant above. Since it is a constant, we're going to set it to 0.5, so basically take half a second to scale out. So that's how we're going to set up these constants here. Now let's go ahead and get away from constants, because that's all we're going to need, and start talking about some of the other fields. We're going to need a static field that is going to hold how many cells have been created. So it's going to be an int, and it's just simply going to be cell count. Because remember, right now, our cells are mixed with our enemies and our player all in the actor list. So I can't just take that list and say, give me a count, because that's not going to be right. What I would need to do without this particular field is take that list and simply loop through it. And every time I come across an entry that was a cell, then I could increment a counter somewhere. And then that's how I could get my count. It'd be a lot easier if we just simply had a field that said, hey, here's our cell count, and we simply increment and decrement this field as cells are created or removed.
It's also more efficient code-wise, because cell count is going to become used in the update method in the game. That means it's going to be accessed 60 times a second.
Exactly.
Now, if cell count was, instead of being a field, if instead it was a method that went through a loop, then we'd have to perform that loop 60 times a second. If we had 60 actors in the scene, that would be 60 times 60 for every update of the game. Or, no, excuse me, for every second that the game was played. Whereas a cell count is just a simple access of a field.
Exactly. Now we've got a cell state, because remember, we made a cell state enumeration above, so now we're going to have a state type that will hold the cell state. So we need to go ahead and make sure we set that variable up. All right, moving on from there, we've got colors. We need a healthy color and we need a dead color. It would be nice if we save those in fields so they weren't hard-coded in, so that we could change them if we wanted to.
Right, so, again, just so that this setting isn't buried down in the cell class, since the color is what I would consider an integral property to the game itself. So what I'll actually do is I'll store the hard values to those back out at the game. And instead, we'll somehow take them into cell and store them in these fields. These fields just keep these variables alive as long as the cell's in existence.
Right.
The other interesting thing is these are going to be instance fields, so if down the road you decide that it would be cool to have different colored cells, it would be very easy to do. Just make sure that as you create cells, you come up with colors to populate.
Exactly. And of course, these two fields are going to be of type color. Now, a couple of more things that we need to worry about dealing with the cell. Cells have the ability to die, which that means they have basically a life, 100% alive or dead, and some percentage along the way as they are being attacked. And then we also need to worry about some means of controlling the rate in which the cell dies. So let's go ahead and set up two private fields, one called life percent, where being at a value of 1 will mean that the cell is 100% healthy, and a value of 0 means the cell is dead. And let's also set up a death rate field, and the death rate field is going to be the number of seconds that it's going to take for a cell to die.
Right. And the idea with using life as a percentage instead of as a point value is that cells are just cells. And the way the game was laid out, all we have are cells, and they all have the same amount of life. Therefore, it's easier to make the health stored in a percentage instead of some arcane point system. So saying that cells have 150 points or some other non-time related amount. So that way we can use life as a percentage, so that if you have a value of 1, the cell is 100% healthy. A value of 0 is 100% dead. And some value between the two is less and less healthy. So that way a value of 0.3 would be 30% healthy.
Right. And then, of course, the death rate.
And just as the name would suggest, that means how fast will the cell die over time. And this is set in seconds. So yeah, number of seconds that the cell will live once attacked. So if the death rate was set to, say, 2, then it would take the cell 2 seconds to go from 100% healthy to dead. So this way, it's a simple means of controlling the amount of time that the cell will live after being attacked.
Exactly. All right, now that we have all of our fields in place, let's take a look at the properties that we're going to need. All right, so for properties, not a whole lot here, fortunately. We need to be able to read the cell state, and we need to be able to read the cell count.
Right, both of these are read-only since the cell state has a lot of things that are tied very closely to it, meaning how much life is left and how time is progressing controls the state. Therefore, we don't want states to be able to be set arbitrarily outside, so we could jump the state or the cell to a state and then have the rest of the timing mechanism break because of it.
Right.
Though we do need to read it, because later when we're trying to do collisions, we want to see, well, is this a healthy cell or is it an attack cell? Because if it's an attack cell, we can save it. So that's something we need to know about a cell. The cell count is also read-only because the cell count is once again defined by how many cells have either been created or died. We don't want this to be set because if you change this value arbitrarily, it will almost always break the code. Because if you set too many cells, then you end up with a case where even though the cells have really actually died, the number is still too high and the code is telling you that it's not, that the cells can't progress. So what will very often happen is you run into a case where you get stuck. So again, both of these are very useful informationally, but need to be read-only so that it's protected and this class isn't easy to break.
Exactly. Now we know we've already got a constructor in place for the cell because we need to pass that texture on up to actor, but we also need to take in a couple of other things. So we're going to revisit the constructor, and we're going to need to make sure that it takes in a healthy color and a dead color.
That's right. Those values need to come from somewhere to populate the healthy color and dead color. And where they're actually going to come from is the game class. So we pass those through the constructor on creation, and we get our field set. And this, obviously, just like all the other classes, is in addition to the texture 2D, since a texture 2D has to come from somewhere to satisfy actor.
Exactly. All right, so that's a look at everything except for methods. So let's look at what methods are going to be required. Good thing I did a new page here, huh, Logan? This ended up being a lot of stuff on this one.
Cell has quite a few things.
Oh, yeah. So for methods, we need to be able to, do several different things. We've got set attack, which is going to be sets the state and the amount of time to die. So, hey, it's attacked. Save. So now it needs to basically set the state that, hey, we've saved, and starts the scale out effect. We, of course, need to override update, which is going to chip away at the life percent and check to see for death, and if the cell has indeed died, handle it. And we're going to have a linear interpolation. I'll talk about that one in a minute. And we're going to have an add cells, just like we had add enemies, so that we can say, hey, add 15 cells. Here's the texture, the healthy color, the dead color. Do it. So, Logan, I'll start out with set attack. And then if you want to just follow me as I walk my way down through these and talk about what they do in a little more detail.
The idea with set attacked is that the attacking timing and mechanism for cells isn't actually defined in the cell class. Instead, it's simply something that can happen to any cell, meaning you can cause any cell to be attacked for pretty much any reason just by calling the method. When calling it, you have to tell it how long it's going to take the cell to die. And again, this is just another convenient point to pass along this value.
That's right.
As a game property.
Okay.
The other thing that means is that the mechanism will have to be outside of the cell class. What's cool, though, is that means you could change this mechanism externally. If somehow you wanted to have multiple cells get attacked at the same time, or even like a kind of enemy that would attack multiple cells, it leaves things very open. And, alright, so next, along with attacked, we need to have some way of saving cells. And this is going to need to do a few things. It'll have to set the state to saved, and then begin that scale out effect.
That's
hitting the cell doesn't make it disappear, it makes it begin a scale. So all of that will be wrapped into the save functionality. And
I didn't mean to do that.
And, of course, in order to get our timing, or the driving force behind all of our time-sensitive code, we're going to need an override to update, so that inside of that we can look at the elapsed time and use that to chip away at how much life is left. And then as we're doing that, see if that had any other further implications, like have we just crossed the 0 health threshold, in which case we've died.
Yeah.
So update is going to need to process life, and it's also going to need to check and see if this has caused a death yet.
So I'll put, and check for cell death. Dun, dun, dun. And if the cell's died, handle it. All right, so next one. Here's a good one. LERP. Oh, boy. Actually, no, this one's not that bad. Linear interpolation between two numbers, two colors.
Well, see, that's
we need basically, as we're dying away, we need to interpolate
right.
between our two colors.
Right. Interpolation meaning just the ability to, what's the word I'm looking for? The ability to take two values, pick a position that is averaged. Not only want to say average, but positioned between the two values.
Yeah, 0 to 100%. Starting at 0, we start at our first value. 100%, we're now at our second value. 50%, we're now 50% between the two.
And the idea is that instead of following the actual percentage, we actually use that in conjunction with real actual values. So that way you have a 0 to 100% value, but you could interpolate, if you wanted, between the numbers 3 and 5.
Right.
So you'd go, that way you could define a more complex scenario where you can have 20% between 3 and 5, which is going to probably yield 3 something or 4 something.
Right. So we're going to use lerp, this method here, for controlling interpolation between our colors from going from a healthy color to a dead color as our cells are dying.
Yeah, really the reason to have this is because lerp by itself, just to interpolate between numbers, is actually already provided.
Mm-hmm.
The math helper class contains that very functionality. The key is that functionality can't be directly applied to a color. It will not work on a color type. So what we're going to do is we're going to use the math helper, and we're going to take in two colors and break them apart, break them into their red, green, blue, and alpha components. Now each of those are just a single number. That number can be used in conjunction with the math helper, and so by breaking that apart into simple mathematical operations, we can take we can take all those numbers and reassemble a new color.
Right.
So it's basically reassembling linear interpolation for color.
And then finally, like we saw, add enemies on the sheet before, we're going to have add cells where we can specify the number of cells that we want to create. We can specify the texture, basically what's needed by the constructor.
So right, a number of cells to create, and then everything else required by the constructor. So we pull in a texture, a healthy color, and a dead color. And then it will otherwise function very much like the add enemies, including the random placement, since that's the idea, is to have a random set of cells on the field.
Right.
Now, of course, this does mean we need to do the check for proper cell placement. That means non-overlapping cell placement. That will have to go hand in hand with the random placement.
Exactly. And that's it. That's everything that we're going to need in place for cells. Whew. All right. So that moves us to our final... Let's go ahead and jump over here real quick to another page. Our final class, which is going to be our bar class. Of course, now I started writing the word class in there, but everybody gets the idea. So with the bar class, what are we going to need? Well, we're going to start out with an enum. Once again, just like we had with cells, we had a cell state enum, but here we're going to have a bar alignment enum.
Right. I found it was convenient to have an alignment system for bars, so that way you could define a bar as center aligned, or maybe left aligned, or maybe right aligned in different cases. Because in watching the game being played when we demoed it earlier, you'll note that the cells have a life bar that is left aligned. That means the point at the left side of the cell doesn't move, and instead the progress bar progresses from right to left. Whereas the time power-up had a time bar that was centered at the top of the screen. That means the left and right edges of the bar kind of move towards each other, towards the center.
Okay.
And now to avoid having any complicated number calculation that has to be done in order for this to happen, it would be much more user-friendly to present an alignment and give that alignment as an enumeration. So that way you can say, well, this bar is right aligned, or this bar is center aligned.
Exactly.
That's a lot more friendly when setting things outside of the bar class.
All right. Fields. Because remember, bar is not an extension of actors. Bar is a brand new class. So what kind of fields are we going to need? Well, we're going to need things like the position. We're going to need an alignment. We're going to need the width, the height, the color, the percent. There's several different things that we need. The texture. And we also need that list, because remember we said that there's going to be a bars list, a static list. It's going to contain all of the bars that we currently have created in our scene. Okay, so let's just go ahead and walk down through that real quick. Position. And this will be a vector 2. We will have an alignment.
And that's just a field to store a bar alignment for each specific bar.
So that's uptype bar alignment. We're going to have a width. Just an int. We're going to have a height, another int. Then we're going to have a color, of course type color. We're going to have a percent. Talk about percent, Logan.
All right, percent is kind of the heart of the idea of the bar class.
That's right.
Because through any relatively simple calculation, you could make a rectangle, and you could figure out how much you want that rectangle to cover, and then define a rectangle with a width that has a width. The key here is to have an original width. So you say at 100%, this bar would maybe cover 200 pixels. But the key is, while leaving width alone, we can adjust the percent. So if we had a width of 200 pixels, but then brought that width down to maybe only 10% of that, we'd be all the way down to 20 pixels in width.
Right.
The key is that we can interface, or we can, use this bar as though it was a progress bar, more or less. So we could say, draw a bar that's supposed to fill up this width. Now chip away at it so that its percentage goes down.
Exactly.
And you actually see the bar deplete as its percentage is lowered.
Okay. And let's see, a couple more, of course. The big one, a texture.
This is interesting because the texture here is going to be static instead of instance. The idea is that bars in this implementation are simply solid colored bars. The texture is used more for a fill color, so the texture itself is generally going to be a white colored texture.
And we're also setting it up as a 3x3 as well.
We'll use this, and we'll use the 3x3 as an alignment. But the texture is going to be stored because we do need some texture to draw from.
Exactly.
So we're going to hold a static field, and that way any bars created can look to their static texture field when they perform actual drawing. Then, of course, another static field we'll need is that list. And this list is used in the same way that the actors list is used. This is a static list of all bars. So that way we keep track of all bars that have been created, and that's useful later when we want to draw all of the bars. We can always look back to this list, iterate through it, and draw any bars as necessary.
Alright, so that wraps up all the fields that the bar class is going to need. So what we'll do now is go ahead and move into the properties of the bar class. We'll take a look at what we need, which is going to allow us to, set some of these things like position, alignment, width, height, and percent. In fact, that's all of them. So we'll have position.
Right, in these cases, these are all simple accessor properties to their relevant fields. Just a way of setting all of the positional information and then including alignment and percent in that.
And finally, percent. Alright, let's go ahead and give myself just a little bit more room. Alright, of course, constructor. We're going to need a static constructor that's going to initialize the bars list, and then a public constructor which will take in things like the width, the height, and the color for the bars. So let's go ahead and put static.
And once again, this is just mimicking the same thing as actor itself. We want some place to initialize the static bars list, so static constructor works well for that.
And then, of course, turn right around and public constructor.
And while we're doing the public constructor, we could probably take in anything that is, well, you could say required for the definition of a bar. And that is things like its width, height, and color.
Okay. And of course, we need to make sure that the public constructor would, of course, add ourselves into the list.
Right, that way any newly...
Same thing we'll see back with actors, too.
Exactly. Any newly created bar automatically gets put into the list, so that way when you're outside of the bar class, simply creating them puts them into that list for easy management.
Right. Now let's go ahead and move into methods. Real simple here. You've already seen something like this back with actors. We're going to have a draw bars, which will contain a loop looping through the static list of bars, calling draw to draw each bar. Okay? And that's it. That is everything that we need to have the bar class skeletoned in, and everything we need to complete an implementation of a skeletoned precision. Okay? Now, is there anything you want to add to this, Logan?
Yeah, in the midst of this many things, no one thing really stands out. But again, the idea here is no Well, I won't say no. I'll say very little actual functionality. When we're skeletoning in the methods, we could do things like knowing that the constructor has to add things to the list. We could do simple things like that. But the idea is to avoid getting into any complicated functionality like any type of time calculations.
Right.
The idea is to define, or just make it so that all of the methods are defined. That could make implementation easier, as those methods will simply be there. And it also starts to put the picture together as to what these things are going to be doing. Even if an implementation isn't provided for each of these yet, we'll know that things like, well, the enemy is going to be able to reset. We'll have it locked in as, okay, at some point we're going to have player reset functionality.
Precisely.
And the same thing for all the other functionality that has been laid out.
Okay. So with that, I guess we can go ahead and get busy and start our first coding phase. So with that, that's going to wrap up this video. Join us in the next video, and we shall begin coding the start of precision.